Is it visible perfectly?
Yes, ma'am.
So we are going to discuss the serial correlation or autocorrelation. Okay. Autocorrelation is also called the serial correlation because mostly autocorrelation is a problem regarding the time series. Okay. In case of time series, mostly we face the problem of autocorrelation. So before starting the autocorrelation, it will be better to understand the context. So I have YT. Y is the output of a particular industry. Y is the output of particular industry. You know, YT is a function of XT. X is the input. Okay, it can be capital, labor, you know, or you can consider X as a vector. So in that case, there are several explanatory variables. Better to say X as a matrix. In that case, actually we are considering several explanatory variables. Okay. However, if you consider this is a single input, YT is a function of XT. So X is capital, say, and Y is the output of iron and steel industry. So iron and steel industry is a function of the capital invested in it. In the first equation, I'm considering the database up to 2021. Okay, because I'm considering the TF period. Okay, so I'm considering 2021 up to 2021, starting from say 1990. Okay, starting from say new industrial policy up to 2021, I'm considering. Okay, and in the second case, when I'm considering YT minus 1, for the same industry, same variables, output of iron and steel industry in India, and X is the capital invested in it. So I'm considering the variables, or I'm considering the observation one less, because it is the regression considering the database up to 2020. It is up to 2021 and this is up to 2020. Now, U consists of effect of explanatory variables which we are not incorporating in a regression model. Error consists of effect of rest of the explanatory variables which we are not incorporating in the model. So if this is the case, the same set of explanatory variables we are not considering for both the equations. We are considering only the capital. However, we are not considering the other raw materials, labor, say, land, say. Now, if X consists of several explanatory variables, 5, 6 explanatory variables, then also if I consider the same set of explanatory variables in two equations, impact of rest of the variables will be captured by the random error term in both the models. Now, if it captures the effect of land, you know, and UT1 is also captured the effect of land on output, in that case, you know, it is natural that UT and UT minus 1 will be related, because same explanatory variable or impact of same explanatory variable has been captured both in UT and UT minus 1. So it is told that though in cross section we may face the problem of autocorrelation, in time series it is inevitable, because for the same sector we are considering time-wise data. For one equation I'm considering a period, for the other equation I'm considering other period. However, the explanatory variables remain same. So the variables which we are not incorporating in the analysis, that also more or less will remain same. If this is the context, you know, it is natural that errors will be related to each other. So it is very, very common in time series analysis. Okay. So when, if any one of you take advanced course, you know, or the special course in the next semester, you have at least some sense of time series in your analysis. So you will find that this is the beginning of the time series analysis. We are starting with the autocorrelation, the concept of autocorrelation in context of time series analysis. Okay, so many a times the autocorrelation is called the serial correlation. Now, I'm dividing the analysis or the sources of serial correlation into two parts. Pure serial correlation, okay? And sometimes because of the problem of model building exercise, serial correlation appears, okay? So first I'm starting with the pure serial correlation, and then I'll move to the context when the serial correlation is appearing because of the model building. Pure serial correlation occurs when classical assumption, which assumes uncorrelated observations of the error term, is violated. So we are assuming that covariance between ui and uj is equal to 0. However, in case of pure serial correlation, this covariance is not equal to 0. There is a correlation between ui and uj. The most commonly assumed kind of serial correlations is first order serial correlation, in which current value of error term is a function of previous value of the error term. Now, if you say there is a relation between ut and ut minus 1 or ui and uj, I need to specify the relation. What type of relation is it? Okay. Now, there are different possibilities. I'll talk about these different possibilities. There is an auto-regressive process, moving average process, auto-regressive moving average process, that is AR, then MA, then ARMA, auto-regressive moving average process. The fourth one is ADIMA, auto-regressive integrated moving average process. So in different ways, the errors can be related to each other. So when I am telling that errors are related, in the next step, I have to specify how the errors are related to each other. So in this context, first, I'm introducing the easiest version, that is first order serial correlation. Ut is a function of ut minus 1 plus a random term. Ut is a function of ut minus 1 plus a random term. If ut is a function of ut minus 1, there is a relation between one order lag that is called the first order autocorrelation. Why autocorrelation? Because it is relation between u and u. It is not the relation between x and y or x and z. It is relation between two u. Therefore, it is auto. Okay. So this is the first order serial correlation. This is basically the AR process. I'll just introduce different processes: AR, MA, ARMA, ARIMA. Okay. So this is the auto-regressive process, first order auto-regressive process. Later I'll specify, this is also called the Markov model, Here U is the error term of the equation in question. That is, in the regression equation, we have this error term, rho, the first order autocorrelation coefficient. Epsilon is a classical error. Epsilon is following all the properties of the classical error. Epsilon is following all the properties of the classical error. That means expectation of epsilon is equal to 0. Variance of epsilon is a constant. Covariance between two epsilon is equal to 0. And covariance between x and epsilon, that is also equal to 0. So it is following all classical properties. The magnitude of rho, that is the correlation, indicates the strength of the serial correlation. If rho is 0, there is no serial correlation. We assume the absolute value of the rho is less than 1. Absolute value of the rho is less than 1. Otherwise, remote past would have more influence on the recent past. Okay, remote past would have more influence on the present than recent past. Okay, now to understand this thing, it will be better to look at different processes. Okay, so this is the general presentation of autoregressive process. This is AR of order K. So here I'm writing the expression as UT is equal to rho 1 UT minus 1 plus rho 2 UT minus 2 plus up to rho K UT minus K plus epsilon T. Okay, so this is the general process. Kth order autoregressive process. Okay, so in the Markov model, I specified only UT is equal to rho 1 UT minus 1 plus epsilon 2 T. Here I am putting rest of the terms. However, the line is not clear. Why I am telling the remote past will be more important compared to the recent past if rho is greater than 1, if absolute value of rho is greater than 1. So we have to do some more things to understand the matter. So let's first check the equations and then only I'll be able to explain why remote past will be more important than recent past if rho value is greater than 1. As I mentioned, in the autoregressive process, this epsilon is a classical term, so expectation of epsilon is 0 and variance of epsilon is a constant. Homoscedasticity. The second or another way by which the present error may be related to different orders of error is the moving average or MA process. I'm writing one multivariate MA of order Q, where UT is equal to epsilon T plus rho 1 epsilon T minus 1 plus rho 2 epsilon T minus 2 plus up to rho Q epsilon T minus K. So here UT is a sequence of classical error. UT, that is present period random error, is a sequence of classical error. Epsilon is a classical error, as I mentioned. The third process is autoregressive moving average, ARMA process, ARMA of order KQ. So here, what I am doing, I am writing this part in the right hand side up to epsilon T. Okay, and from epsilon T, I'm also starting to write the MA process. So rho 1 UT minus 1 plus rho 2 UT minus 2 plus up to rho K, there will be a plus sign, rho K UT minus K plus epsilon T plus rho 1 star epsilon T minus 1 plus up to rho Q star epsilon T minus Q. So it is the joint function of AR and MA, ARMA. Now there is one more process which we call ARIMA, autoregressive integrated moving average process. That process is a bit complicated rather than simply adding the two series. And for that matter, I'm not introducing that series in this course. So I'm writing AR, MA, and ARMA. In our due course, we will find that 1 and 2 are required for this class. The AR process and the moving average process. AR process and the moving average process. Okay. Now look at the AR1 process. UT is equal to rho UT minus 1 plus epsilon T. A very simple finite process which we call the Markov model. AR1 process. Now UT minus 1 following the same logic is rho UT minus 2 plus epsilon T minus 1. What I am telling that if UT is equal to rho UT minus 1 plus epsilon T, UT minus 1 if we write, that will be equal to rho UT minus 2 plus am I right? Can we write this thing without losing any generality? If UT is equal to UT minus 1 plus epsilon T, in that case UT minus 1 is rho UT minus 2 plus epsilon T minus 1. Okay. Following the same logic, UT minus 2, that is equal to rho UT minus 3 plus epsilon T minus 2, and so on. So in place of UT minus 1, I can replace rho UT minus 2 plus epsilon T minus 1. So I'm getting epsilon T plus rho epsilon T minus 1, epsilon T from here, epsilon T, rho epsilon T minus 1, rho epsilon T minus 1, then rho square, and then UT minus 2 can be written as rho UT minus 3 plus epsilon T minus 2. So the things will go on like this, and finally we will get epsilon T plus rho epsilon T minus 1 plus rho square epsilon T minus 2, from here rho square epsilon T minus 2, and so on. Finally, rho to the power T epsilon T minus T, which is 0. So rho to the power T epsilon 0. So AR process can be presented in this format. Okay. UT is equal to this. So if this is the fundamental behind AR1 process, first I am getting rho, then I am getting rho square, then I'll get rho cube, and finally I'll get rho to the power T. Now if mod rho is greater than 1, in that case, this value will be greater compared to this one. And finally, this value will be highest. It will be greater compared to any other value, rho, rho square, rho cube, etc. Am I right? Suppose rho is 5, then 25. The thing will increase in this way. Am I right?
Yes, ma'am.
Yes.
Okay. So in that case, T minus 2th period will have more impact on UT compared to T minus 1th period. T minus 3rd period will be again more important compared to T minus 1 and T minus 2. And, you know, the last period, you know, that is very, very remote past. That remote past will be important compared to any other time period. That is the 0th period, initial period from where I started. That 0th period will be very, very important, you know, most important compared to any other things. Now in empirical analysis, generally we find that recent past has more importance or more impact on present compared to the remote past. Okay. If you look at the financial situation of the country, if you look at the market behavior, if you look at the trade pattern, I hope you will agree with the matter. Recent past has more impact on the present compared to the remote past. Will you agree?
Yes, ma'am. Yes, ma'am.
Okay. So if you agree with this matter, what will be the rational value of rho? Greater than 1 or less than 1?
Less than one.
Less than 1. Because in that case, if it is a fraction, in that case, if you go for rho square, the value will be reduced, rho cube reduced as you are moving towards high value, if you consider a long series, for 50 years, etc. For the 50th period, if you consider the lag of 50 years, so that will have a very small impact on the present value of the variable. Okay. So therefore, it is rational to consider mod rho to be less than 1 so that we can prove that, or we can establish that recent past will have more impact on present compared to the remote past. And this is very rational. It's not that it is a stringent criterion. Stringent criterion will be that one if we consider the remote past has very, very importance to determine what will happen in the present period. Okay. So, as I started to tell you, the mod rho value should be less than 1. Otherwise, the remote past will have more influence compared to the recent past. Okay. Another problem, if mod of rho is not less than 1, the variance would explode to infinity. If mod rho is greater than 1, variance would explode to infinity. This point I'll explain later when I'll talk about what will be the variance, etc. So I'm keeping this point, in this slide, and I'll explain this point later. The sign of rho, first I told you something about the value of rho. Now I'm telling you about the sign of rho. It can be positive, it can be negative, okay? So the sign of rho indicates the nature of the serial correlation in an equation. Positive serial correlation implies that error term tends to have the same sign from one time period to the next. In T-1th period, same trend. If it falls, it falls for last few periods. If it increases for last few periods. So this kind of thing, movement will be in the same direction. Negative rho means that error term has tendency to switch signs from negative to positive, positive to negative, etc. Okay, so let's try to understand this graphically. Along the horizontal axis, we are measuring time. Okay, so I have time corresponding to this. I have time t. Now corresponding to this, say t plus 1. Corresponding to this, t plus 2. Okay. So this is the value, this is the value of error in the first period, this is the second period, third period, etc. So if I consider a correlation between these two error terms in two different time periods, both are moving to the same direction, both are falling. So correlation will be positive. If you consider this and this, both are falling. So correlation will be positive. Next, if you consider this and this, they are moving in the same direction, rising, rising. In this direction, they are changing. So they are changing in the same direction. There is U kind of thing. So coming to this juncture, if you consider the time-wise data, the trend is positive. Here, if you consider the time-wise data, time-wise error term, error, we are measuring along this axis. Time we are measuring along this axis. So time-wise errors are moving in same direction. Here, time-wise errors are moving in the same direction. So this is the sign of positive. This is the sign of positive serial correlation. Now, this is also the sign of positive serial correlation. If you consider the time-wise thing, this is the first period error. This is the second, so increasing. Coming at this juncture, time-wise, they are falling. They are falling. Okay? So if I have this kind of thing, there is positive serial correlation. This is the diagram for no serial correlation. I am not understanding anything. Time-wise, what is happening, that I am not understanding. Because in the first period, it was here, In the second period, it is here, third here, fourth here, fifth here, or fifth here, sixth here, seventh here, sorry, this is seventh one. So what is happening, that is not clear. So no clear trend here. So it is no serial correlation. Now here, systematically, on Tth period, I am getting this. Plus 1, T plus 1, this. T minus 1, this. Sorry, T plus 2, this. T plus 3, this. T plus 4 here. T plus 5 here. So a systematic zigzag. In one period, the value is positive. In the second period, the value is negative. Third period, positive. Fourth period, negative. So if I consider the time-wise correlation, it is the diagram showing negative serial correlation. Okay. This is also negative serial correlation. This is the first period error. This is the second period error, third period error, fourth period error, fifth period error, sixth period error, seventh period error. Okay. So zigzag like this. So this is the diagram again for negative serial correlation. So correlation may be positive if, over the time, errors move in the same direction. At least for the certain time period, errors move in the same direction. In that case, there is positive autocorrelation. If there is no pattern, then rho is equal to 0. If time-wise, in the first period, error is positive, in the second period, negative, positive, if moves like this, this is the evidence of negative serial correlation. Is it okay to all of you? Any question, any query, any clarification you need?
Could you re-explain no serial correlation?
When you cannot understand any pattern, simply, random things, you are not understanding. Period-wise, there is no, period-wise analysis is not possible. Okay?
Okay, ma'am.
If the errors are purely random, in that case, it is the classical error. Such error terms would conform, there is a mistake, to classical assumption. Classical assumption. Classical assumption of no autocorrelation. Classical assumption of no autocorrelation. Okay. Next, I am telling you something about the impure serial correlation. Serial correlation is appearing, however, not from the data. Pure serial correlation is appearing from the data itself. Here, in case of impure serial correlation, from the data, the correlation is not arising. It's not that for the matter of the data, there is correlation. Rather, there is some problem in the model building, and for that matter, the serial correlation is appearing. Impure serial correlation is serial correlation that is caused by specification error, such as there may be some omitted variables in the regression, important omitted variable, or we may consider the incorrect functional form. Omitted variables or incorrect functional form. How does this happen? Let's consider an example. Y is a function of two explanatory variables. Demand is a function of price and income. Two very important variables. Epsilon t is a classical error. If x2 is accidentally omitted from the equation, or if data for x2 is not available for the time, then, a researcher is writing the model as yt is equal to beta naught plus beta 1 x1 t plus epsilon t star, where epsilon t star is capturing the effect of x2. x2 is very important variable. We know always it will have impact on yt. Income will always have impact on yt. However, I didn't consider income. So naturally, the effect of income on demand is there in the random error term. So random error is not then a classical error. It is beta 2 xt because x2t is really important. Beta 2 x2t plus epsilon t. Beta 2 x2t plus epsilon t. Okay, this is the true model. So if I write the true model in this form because of any reason, so naturally error of the model I have written for that, the error is basically the component which I should have in the true model and the error of the true model. So the error term is not a classical error term. Instead, the error term is also a function of one of the explanatory variables x2. As a result, the new error term epsilon star can be serially correlated even if the true error term epsilon is not. Okay. Now, if I consider the two separate regression equations, for I observations and j observations, because of the fact that I missed an important variable in my regression in both the context, for both the cross section, in that case, the errors of the two cross section will be related. I'm collecting data from West Bengal and Bihar. And in the demand equation, I'm not considering income, which is really important, which should be there in the true equation. So the error term of Bihar and West Bengal will be related to each other because it is capturing the impact of income on demand. In particular, the new error term will tend to be serially correlated when X2 itself is serially correlated, this is quite likely in a time series. And in case of cross section 2, under certain circumstances, the two errors will be related, and the size of epsilon is small compared to the size of beta 2 X2 bar, so that epsilon cannot randomize the entire thing. Now, if it happens, if this epsilon is large, and it is random, sometimes, the impact of this part we can overlook. However, if this component, the random component, is lesser, small, compared to this part, in that case, no way we will be able to overlook X2T. It should have some problem. It will generate some problem in the context. It will generate the problem. So this is the thing. So X2, if X2 is serially correlated, naturally the two errors will be related. And or if random part is smaller compared to the impact of X2, in that case also there will be some problem in the error term. Error will be no more the classical error. Okay, so this is the presentation of disposable income, which is a function of time. Income is a function of time. Whatever be the level of income, it slowly increases. Consumption slowly increases. Saving function slowly increases. So there is a time trend in most of the macro data. There is a time trend involved inherently in most of the macro data. So somehow, if you miss this variable, which is an important in your research purpose, naturally, it will be there in your error term. And since these macro variables are related with time trend, it will cause serial correlation in your analysis. Because these variables by nature, are related with some time trend. Okay, all these functions increases slowly over time. So a time trend is involved in these variables. Okay, so if you consider a model where you are missing, say, income, per capita income, or per capita consumption, or per capita savings, this may result in autocorrelation. Okay. The next is incorrect functional form. I mentioned there are two sources. One source is the omitted variable, important variable, you omit it. And that important variable may be serially related. Or that variable may be, greater than the random error component. So this part was the first part in the impure correlation part. Now the second source is incorrect functional form. Suppose the functional form should be like this. The relationship is, parabolic. The relationship between y and x is parabolic rather than linear. It is parabolic. However, instead of considering the polynomial, you are considering the linear relationship. Yt is equal to alpha naught plus alpha 1 x1t plus epsilon t star. The new error term epsilon star is now a function of true error term and of the difference between the linear and polynomial functional forms. So epsilon t star consists of this epsilon t plus this part. Okay. So if this is the case, in that case also, you will face the problem of autocorrelation. You will face the problem of autocorrelation. Okay. And if specifically this x variable or x1 variable is a time-bound variable, then inevitably there will be the problem of autocorrelation. Okay. So actually this is the true functional form. However, you are fitting a linear curve. Okay, so this possibility I'm talking about, wrong functional form you are considering. Instead of considering the parabola, you are considering the linear relationship. So if this you do, this can be another source of impure serial correlation. This is another example, if you consider a linear fit here, that will give you a serial correlation. Are the things clear to all of you? Sources of autocorrelation? What is meant by
Ma'am,
sources of autocorrelation? Yes?
একবার ওই 5B স্লাইডটা যাবেন? হ্যাঁ হ্যাঁ।
Okay, here also you can draw the feet, like this. Okay, so it is not capturing the essence of the data. Got it?
Yes, ma'am.
Now, once we understand what is the serial correlation, how we will present it using different processes, AR, MA, ARMA, etc. Next, we will go for the consequences of autocorrelation. What will happen if I estimate the parameters of the regression model using the ordinary least square technique? Now, to understand the consequences of the serial correlation, we will consider the pure serial correlation problem. Okay, pure serial correlation problem. Henceforth, mostly we will concentrate on pure correlation problem, because I didn't cover the omitted variable misspecification to that extent, so that you will understand all steps. Okay, so these parts are due: the omitted variable part, misspecification part. Okay, analysis, considering all these things are due, because we can do all these things, as we introduce a multiple regression. If we increase the number of explanatory variables in the model, then only we can go for meaningful discussion regarding the omitted variable. I hope you are understanding. If I omit something and still estimate a regression model, you need more than one explanatory variables. If you have a single explanatory variable in your model, okay, I will not have any variable at all if I omit something. Okay, so for misspecification also, we need to introduce the multiple regression first, and then I'll be able to talk about all these parts, all these sections. So henceforth, I am concentrating on pure serial correlation. The existence of serial correlation in the error term of an equation violates classical assumption of non-autocorrelation. And the estimation of the equation with OLS has at least 3 consequences. Number 1, pure serial correlation does not cause bias in the coefficient estimates. So this is similar to that of the heteroscedasticity problem. In context of heteroscedasticity too, we proved that presence of heteroscedasticity does not disturb the unbiasedness property of the estimator. Beta hat OLS is still an unbiased estimator. Similarly, in presence of autocorrelation, we can prove that beta hat OLS will be an unbiased estimator of beta. However, serial correlation causes OLS to no longer be the minimum variance estimator. It will no longer be a minimum variance estimator. Okay, so there will be again problem regarding the variance calculation of beta hat OLS. as we calculate variance of beta hat OLS in presence of autocorrelation, we will not get the variance value to be sigma square by summation xi minus x bar whole square. It will be something else. Third, serial correlation causes OLS estimates of the standard error to be biased, leading to unreliable hypothesis testing. The standard t value is given by beta hat divided by standard error of beta hat. If the standard error of beta hat is disturbed because of presence of autocorrelation, naturally you will not get the reliable t statistics. Okay, so t values will become unreliable in presence of autocorrelation. Okay, so unbiasedness property of the estimator will be retained, minimum variance property will be disturbed, and as minimum variance property is disturbed, standard errors are not the true standard errors, no more. These are the standard errors related to BLEU, best linear unbiased estimator. Hence, the t statistics are becoming unreliable. Okay, so we have to prove all these things. We have to prove the first 2 points. The estimator is unbiased, however, the minimum variance property is not retained. Now, if I can prove this problem, or if I can present this issue, the next step will be how we will go for some remedial measure so that we get back best linear unbiased estimator. In presence of heteroscedasticity, I talked about WLS estimator, weighted least square technique. Though WLS has some limitation, however, it is well accepted technique in presence of heteroscedasticity. If WLS is not applicable, we will go for GLS. Okay. However, WLS, GLS, these are very well accepted technique. Now, in presence of autocorrelation, if we prove that OLS does not work or OLS does not produce BLEU or MVUE, minimum variance unbiased estimator, we need to learn what can be an alternative technique which can give us the best linear unbiased estimator given the data set. Okay. And we need to learn several tests by which we will be able to detect autocorrelation. Okay. In case of heteroscedasticity, we discussed about a number of tests: Glaser test, Goldfeld-Quant test, Ramsey reset test, So different types of tests, Bruch-Pagan-Godfrey test, by which we will be able to detect heteroscedasticity problem. In context of autocorrelation, we will learn about Durbin-Watson technique, DW technique. Durbin-Watson technique to detect the problem of autocorrelation. There are several other techniques too, because again, Durbin-Watson has limitation. However, it is well accepted. It is widely used, So we will learn about the technique and we will also learn what are the limitations of DW test, sorry, to detect autocorrelation. Now, before going to these parts, detection, remedial method, first we want to prove 1 and 2. It is still giving unbiased estimator and it is not giving best estimator. Already I told you about the AR1 process, which is equivalent to MA infinity. Okay, moving average infinity. Because this process, the simple AR1 process can also be presented as summation j is equal to 0 to infinity rho to the power j epsilon t minus j. So the equivalence already I discussed, this you have to keep as a note, because when I'll try to prove the beta hat OLS is an unbiased estimator, and or I'll try to find out the variance, this I need, because here I can present UT in terms of all classical error. UT can be presented by MA infinity process. Now, MA process consider a number of classical error epsilon. So I need this relation to present different consequences of autocorrelation. Okay. So this relation itself is very, very important. The Markov model is very important, and the presentation of Markov model in terms of moving average infinity scheme, that is also very, very important. Okay, so before finding the properties of beta hat, first we need to present the error term in terms of autocorrelation, etc. When I'm following this process, UT is equal to rho UT minus 1 plus epsilon T. So what will be structure of my expectation of UT, variance of UT, etc. So my regression model is say okay. So instead of I am writing T. Yt is equal to beta naught plus beta 1 xt plus ut. This x is capital. Okay. And I am also writing so this pair of equations are there to begin with. This is my original regression model, and this is the presence of, this is showing the presence of autocorrelation. Now for this model, expectation of UT is equal to 0. Variance of UT, okay, just look at this one. I have summation j is equal to 0 to infinity rho to the power j epsilon t minus j. So variance of UT, if I consider variance of UT, that will be equal to variance of this summation. Okay. Now, since variance will give us the square terms, so it will be rho to the power 2j, and expectation of these epsilon t minus j square, which will give me the variance of this part. Okay. So from this we will get rho to the power 2j, and from this we will get variance of epsilon t minus j. Variance of epsilon t minus j, that is sigma epsilon square, a constant, because epsilon is a classical error. So I can bring this sigma epsilon square outside the range of sum. So if you look at this, it is summation j is equal to 0 to infinity rho to the power 2j, variance of or expectation of epsilon part, that is a constant given by sigma epsilon square, so that we can keep outside the range of sum. So it can be presented in this way. Sigma epsilon square multiplied with 1. If you said j is equal to 0, rho to the power 0, which is 1. Okay. Okay, so there is a mistake. There is a mistake. This row will be not here.
ম্যাম একটা হ্যাঁ
Yes. This row will be not here. It will be 1 plus rho square plus rho to the power 4. That is, there will be a GP series. This is a GP series. Okay. So it will be 1 plus rho square plus rho to the power 4, etc. So I am getting sum of GP series. So the value is sigma epsilon square by 1 minus rho square. Now rho will be a numerical figure. It is the correlation between the two error terms. So this can be considered as a constant. This term is a constant. So this can be presented as sigma u square, and this is proving that for this pair of equations, homoscedasticity prevails. For this pair of equations, homoscedasticity prevails. So when I am considering autocorrelation, and if I consider this set of equations that is not disturbing the variance of the error term, variance of error is still a constant, so it is homoscedastic. Any question? Expectation of ut is equal to 0 and variance of ut a constant. Any question for these two?
ম্যাম
Yes.
ম্যাম সামেশনের মানে আমি যখন ভেরিয়েন্সটা নিচ্ছি তো তখন ওটা সামেশন পি পিজে পি টু দি পাওয়ার জে স্কোয়ার কেন হয়ে যাচ্ছে মানে পি টু দি পাওয়ার টু জে কেন হচ্ছে
ভেরিয়েন্স তো স্কোয়ার করে দেয় না, তোমার তো এটা যা ছিল রো টু দি পাওয়ার জে, ভেরিয়েন্সটা তো হোল স্কোয়ারের মতো, তাই না? ধরো ভেরিয়েন্স অফ এ প্লাস বি এক্স আই, এটার ভেরিয়েন্সটা কত?
আচ্ছা এটা স্কোয়ার হ্যাঁ 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 স্কোয়ার চলে আসছে বুঝতে পেরেছি
বলো আমাকে ভেরিয়েন্স অফ এ প্লাস বি এক্স আইটা কত?
ভেরিয়েন্স অফ
এ প্লাস বি এক্স আই, দেখো লিখেছি,
ম্যাম
কবে লিখতে পারি?
ম্যাম ওই ইয়ে এ এ মানে এ প্লাস বি এক্স আই এর স্কোয়ার টার্মস এর ভেরিয়েন্স গুলো বেরোতে থাকবে
না, কনস্ট্যান্ট টার্মের তো ভেরিয়েন্স হয় না।
বি স্কোয়ার বি এক্স
ম্যাম ওটাই তো স্কোয়ারটা বেরোবে, এ স্কোয়ার বাইরে যাবে।
এই রেজাল্টটা হবে রাজদীপ, ঠিক আছে?
হ্যাঁ ম্যাম
এইগুলো একদম ভালো করে বুঝে নিতে হবে। ভেরিয়েন্স অফ কনস্ট্যান্ট ইজ 0, whereas variance of bxi will be b square variance of xi. ঠিক আছে? মানে variance of a bxi ফার্স্টে লিখবো variance of a plus variance of bxi plus 2 covariance between a and b, okay, or a and bxi, যাই হোক লিখছো, ওই কোভেরিয়েন্সটা 0। সো ভেরিয়েন্স অফ a প্লাস bxi, এটা ভেরিয়েন্স অফ a প্লাস ভেরিয়েন্স অফ bxi করে এইটা 0, আর এইটা হয়ে যাচ্ছে b স্কোয়ার ভেরিয়েন্স অফ xi, ঠিক আছে? তাই জন্য ওইখানে রো টু জে হয়ে যাচ্ছে, রোটার রো জের স্কোয়ার হয়ে যাচ্ছে, রো টু জে হয়ে যাচ্ছে।
আমাকে আগের স্লাইডটা দেবো। ওটা কোভ্যারিয়েন্স দিয়ে ওটা কি লিখেছেন ওই প্লাস
সাধারণত তুমি যদি ভেরিয়েন্স করো তাহলে তো a প্লাস বি হোল স্কোয়ারের মতো হয়, তাহলে কোভেরিয়েন্স টার্ম গুলো আসতে থাকবে।
আচ্ছা
কোভেরিয়েন্স তো এখানে দুটো ভেরিয়েবল ফার্স্ট অফ অল নেই, তোমার একটাই ভেরিয়েবল আছে xi,
হ্যাঁ 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 হ্যাঁ
তাই জন্য এই পার্টটা 0, মানে এই পার্টটা লিখতে হবে না,
ও আচ্ছা আচ্ছা
ঠিক আছে?
হ্যাঁ
আর যদি দুটো ভেরিয়েবল থাকতো তোমাকে ইন্ডিপেন্ডেন্স ধরে নিতে হতো। তুমি যদি শুধু ভেরিয়েন্স লিখতে চাইতে তাহলে ভেরিয়েবলস আর ইন্ডিপেন্ডেন্ট তোমাকে ধরে নিতে হতো। ওকে, আগের ক্লাসে দেখো যত নরমালের টেস্ট এগুলো করেছি, টু ইন্ডিপেন্ডেন্ট ভেরিয়েবল পরিষ্কার লেখা আছে, আদারওয়াইজ দ্য কোভেরিয়েন্স টার্ম উইল অ্যাপিয়ার। আচ্ছা, তাহলে ভেরিয়েন্স অবধি ক্লিয়ার। নেক্সট, please concentrate, it's a big calculation, please concentrate. Very notational and a big calculation, however the thing is very easy, very simple. Covariance between two error terms, say UT and US. Both T and S are running from say 1 to n, however T is not equal to S, this kind of thing. So covariance between UT and US. Now UT I can write as an MA series, epsilon T plus rho epsilon T minus 1 plus rho square epsilon T minus 2 up to, it is continuing. Okay, infinite MA series. Now in between I am bringing S. In the first series, the T series, I am also bringing S. S is another number, so I am also putting T minus S. So epsilon T minus S, rho to the power T minus within bracket S minus 1, which is T minus S plus 1. So epsilon T minus within bracket S minus 1, which is T minus S plus 1, if you open the bracket. So this thing will be the part of UT. So first eta dekho whether you are understanding this series or not. This series.
ম্যাম,
Yes.
মানে আমরা এখানে বেসিক্যালি ওই এরর টার্মটাকে ওই ক্লাসিক্যাল এররের মানে ইনফিনিট সিরিজের জন্য লিখছি, দুটো টার্ম ইউটি আর ইউএস দুটোকে এক্সপ্যান্ড করে ওই ফর্মটাতে লিখছি।
হ্যাঁ, মানে UT and US are expanded following the MA infinity series.
রাইট ম্যাম, গট ইট।
Because always I mentioned you have to bring the things in terms of epsilon, because epsilon is a classical error. You will be able to apply different properties of the classical error on epsilon, not on U. Okay, so for US, I am writing the series as epsilon S plus rho epsilon S minus 1 plus rho square epsilon S minus 2. So things are going on like this. Okay. Now remember, epsilon is a classical error. So am I right? If it is a classical error, covariance between two different epsilon, that will be absolutely equal to 0. Okay, so covariance between epsilon T, epsilon S, epsilon T, epsilon S minus 1, epsilon T, epsilon S minus 2, etc. all are 0. Similarly, covariance between epsilon T minus 1, epsilon S, epsilon T minus 1, epsilon S minus 1, T minus 1, S minus 2, everything is 0. Following the same logic, epsilon T minus 2, epsilon S, T minus 2, S minus 1, all these things are 0. Now come here at this juncture. Epsilon rho to the power T minus S. Now here T minus T plus S. So there is epsilon S. Epsilon S. From here, you are getting epsilon s. From here, what you are getting? If you adjust,
epsilon s minus 1.
epsilon s minus 1. Everybody? So there is a situation, rho to the power t minus s epsilon s, covariance between this rho to the power t minus s epsilon s and this epsilon s. This thing. Okay. Now, if I consider covariance between epsilon s and epsilon s, what does it give?
Variance.
Variance. Covariance between the two same variables basically gives us variance. Okay? Because we are considering epsilon square s. So it is the variance. Now it is a classical error. So the variance will be nothing but sigma epsilon square. So it is rho to the power t minus s sigma epsilon square. Okay. Next, if I consider this, rho to the power t minus s plus 1 and epsilon s minus 1. So this epsilon s minus 1 here and epsilon s minus 1 here. So again, covariance between the two epsilon s minus 1 will give us the variance sigma epsilon square, constant variance sigma epsilon square. Cofactors are this rho and this rho to the power t minus s plus 1. So when we will have the common terms between the series, epsilon s minus 1, epsilon s minus 2, the common terms, we will have this kind of sum. That is, for the variance part, we will get these values. Okay. So I can take this sigma epsilon square common, and I can take rho to the power t minus s also common, and I'm left with 1 plus rho square plus rho to the power 4, etc. So if you understand this step, the next step is easy. Sigma epsilon square rho to the power t minus s and the sum of the GP series. 1 by 1 minus rho square. This term is not at all 0. It is very clear. This is something which is not equal to 0. Hence, there is correlation between UT and US. Covariance is not 0. So there is a correlation between UT and US, and that is presenting the presence of autocorrelation. This is no more equal to 0. This is equal to this number, sigma u square rho to the power t minus s, which is not 0. So, in presence of autoregressive process of order 1, simple series, Markov model, only the first order lag. However, we are getting the presence of autocorrelation. Okay, so non-autocorrelation assumption is disturbed if we consider this pair of equations. Non-autocorrelation assumption is disturbed if I consider non-autocorrelation assumption. Any question, any clarification, any repetition you need? Yes.
Could you explain how in that second step, the second term in a sum, how it's rho times rho t minus s plus 1
Okay.
times sigma e squared?
Yes. We are taking covariance between rho to the power t minus s epsilon s and rho epsilon s minus 1. Sorry. I'm taking the correlation between this one you are asking for, I think. Right?
Yes, ma'am.
So I am considering this term and this term. Okay. So there is rho to the power rho to the power t minus s plus 1 into epsilon s minus 1. And here you have rho epsilon s minus 1. Now, when you are taking covariance between epsilon s minus 1 and epsilon s minus 1, you are getting the variance. Okay. The cofactors are rho and rho to the power t minus s plus 1. So, rho and rho to the power t minus s plus 1. This you are getting. The cofactors only. This cofactor and this cofactor. Rho from here and rho to the power t minus s plus 1 from this term. Okay, are you getting this?
Yes, ma'am. Got it.
Any other question, any clarification, anything you need?
So, ma'am, when we are taking the covariance like that, so we take the rho t minus s plus whatever part from the earlier segment and rho squared or rho cubed from the epsilon s segment,
Yes.
right?
Because expectation will be operated on epsilon part only. So constant terms will come out.
Yeah.
Okay. So it is basically rho into rho to the power t minus s plus 1 expectation of epsilon s minus 1 and epsilon s minus 1 or epsilon square s minus 1. And from there you are getting the variance. Okay. Rajdeep, Abhishek,
Yes, ma'am.
Darpok. So you are understanding the things?
Yes, ma'am.
Because rest of the people are a bit shy to ask the questions, So if you have some questions, please ask, So rest of the classes will be also benefited. Pratush,
Yes, ma'am.
understanding the things?
Yes, ma'am. Understanding.
Okay. So you have to do these things in your copy, because this part is bit notational. The things are not difficult. However, long notations are there, equations are long, and for that matter, you need to write the things. So the nature of the error or characteristic of the error part is complete in presence of the set of equations we have considered. Next, I have to come for beta hat. So let's consider the same model, yt is equal to beta xt plus ut. You may consider the intercept, you may not consider the intercept for the time being. For time being, I'm not considering the intercept because, My focus will be on the regression coefficient beta hat OLS. I don't want to, calculate the intercept term too in this case. So for that matter only, I'm considering this kind of equation, the line passing through the origin. The OLS estimator for beta will be summation xt yt divided by summation xt square. So, some of you did this exercise during your Viva. For rest of the students, you may try. What will be the value of beta at OLS when the equation is given by yt is equal to beta xt plus ut? That is a line passing through origin. Okay, so that this part I'm keeping for you. So this you derive. Now, once I find beta hat OLS is summation xt yt divided by summation xt square, yt can be substituted by beta xt plus ut, as we are doing repetitively for all cases. So, if I substitute this yt, this part, by beta xt plus ut, so summation xt square you will get from this part. Beta you can keep outside the range of sum. So summation xt square and summation xt square will be cancelled and you will simply get beta. For the second part, you will get summation xt ut divided by summation xt square. Now, if this is the format of beta hat OLS, and if you take expectation of beta hat OLS, it will be expectation of beta plus summation xt expectation of ut divided by summation xt square. So this second part will be equal to 0 as expectation of ut is equal to 0. Okay, so expectation of beta hat OLS is still equal to beta. So unbiasedness property is retained. Unbiasedness property is not disturbed in presence of autocorrelation. It is not disturbed at all. Next is variance of beta hat OLS. Okay. So I'll stop with this slide. I'll not proceed further. So, there are a set of equations and derivations, However, this is the last slide for today. So variance of beta hat OLS. Now for calculation of variance of beta hat OLS, the formula is I hope by this time you are understanding this is actually expectation of beta hat which has been substituted by beta, because already I proved beta hat is an unbiased estimator of beta. Okay. Now beta hat minus beta, that is summation xt ut divided by summation xt square. So in place of beta hat minus beta, I'm putting this value. So if I go back, beta hat minus beta, so there is beta hat. So beta hat minus beta is nothing but this part. Okay. So I am using that. Beta hat minus beta is summation xt ut divided by summation xt square. So in the variance formula, I'm putting that. Now xt is non-stochastic. So I can keep this outside the range of expectation. So I'm putting it here. Then I am considering summation xt square expectation of ut square. So I'm getting from this expression, as you know, this is actually a plus b plus c plus dot dot whole square of this thing. So a square plus b square plus, square of all terms plus 2ab, 2bc, all these kinds, all these expressions will be there. Okay. So all the whole square I am keeping here. Summation xt square ut square. And then if I operate expectation on the random part, it is summation xt square expectation ut square. And then 2 summation xt ut xt minus 1 ut minus 1. So I am clubbing xt minus 1 part and clubbing ut minus 1 part and operating expectation on that. Then plus 2 summation xt minus 2. This is tet minus 1, then tet minus 2. Expectation ut minus 2, and the expressions will go on and on. Okay. Now, already we proved that variance of ut is equal to sigma u square, homoscedastic. Covariance is sigma u square rho to the power s. Okay. It is not equal to 0. So it is something like this. So now, in the expectation of ut square part, I can put this variance of ut, that is sigma u square value. And in places of expectation ut minus 1, ut minus 2, I'll substitute these values. Sigma u square will remain unchanged. However, the power of rho will change depending on the lag. Okay, so sigma u square in this place, I am putting summation xt square sigma u square. In rest of the space, I am putting, in place of expectation of ut minus 1, I am putting sigma u square rho to the power s. So sigma u square is everywhere. So I can take sigma u square common. So sigma u square divided by summation xt square. This part I am keeping here. So rest of the things are summation xt square plus 2 here first order lag. So rho summation xt minus 1, because the expression is summation xt minus 1 expectation of this part. So here there are two components, rho sigma u square. Sigma u square I am keeping outside as a common factor, and rho here. Following the same logic, plus 2 rho square, because here I have rho square sigma u square. So sigma u square outside and rho square here. Summation xt minus 2 is already there. Okay. So if I take this common, okay, and if I divide the rest of the series by 1 summation xt square, here there is a square. So I am keeping summation xt square here, and dividing all the rest of the parts, by another summation xt square. So I can present the thing in this way. Actually, I do this to make the terms easier. These are correlation kind of thing between xt and xt minus 1. Okay. So we can write it as R1, R2, etc. So later I'll do that. However, to do this thing, we just arrange the things in this way. If you can write up to this step, then also it is fine. However, if I write the step in this way, we are getting the OLS variance here. This is the formula for OLS variance. Sigma square divided by summation xt square. This is the OLS variance, which is multiplied with this non-zero term, with this term. Okay, with this term. So I hope you are understanding this is not equal to sigma square by summation xt square. Okay, which should be the formula for the variance for this model. Yt is equal to beta xt plus ut. The variance will be sigma squared by summation xt square. This also you calculated, some of you calculated during your viva, rightly calculated. Okay, so we are getting the variance of beta hat OLS is original or the best variance into something. So definitely it is greater than that of the variance we get in a classical model. So please tell me whether you are understanding the steps, whether you are understanding the logic, and if you understand the logic, I'll be able to state, so beta hat OLS is no longer the best estimator. So the blue property is violated. Blue property does not hold. Blue property is violated. It is unbiased estimator. However, it is not the minimum variance estimator. The variance is greater than that of, I cannot say greater because the correlation between xt minus 1 can be negative, etc. So it is not the perfect one. It is not the best value. It is something else. Any question?
Ma'am, could you go back to the covariance slide, the covariance of UT, US?
Yes.
ম্যাম এখানে কোভেরিয়েন্স অফ ইউপি ইউএস টা আপনি লিখেছেন রুট টু দি পাওয়ার টি মাইনাস এস, আর ওখানে গিয়ে আপনি লিখেছেন শুধু এস, ওটা কেন?
ওটা একটু সিম্পলিফাই করে লিখেছি।
আচ্ছা,
you can write t minus s2. Okay, now if you consider, t is the range of time, say 50 years. S is also range of time, say 25 years. Okay, so it is a numerical figure, nothing else.
আচ্ছা বুঝতে পেরেছি।
Power of rho is a numerical figure. Okay.
Yes, ma'am.
Okay.
Ma'am,
Yes.
ma'am, in these expressions, the xt terms are in the deviation form, right? Or is it like
Yes,
a
ma'am.
notation?
Plus small x হবে।
I didn't get your question.
ম্যাম ওই যে আপনি যেগুলো ক্যাপিটাল এক্সটি লিখেছেন এখানে, ওই টার্মগুলো স্মল এক্সটি হবার কথা তো।
না না, কেন ডেভিয়েশন ফর্মে ধরবো কেন? আমি একটা ইকুয়েশন ধরতে পারি না, পাসিং থ্রু অরিজিন, হয় না এরকম?
ও আচ্ছা
ডেভিয়েশন ফর্ম কেন সব সময়? I can consider a model without the intercept term. সবই ক্যাপিটাল, এখানে স্মল নেই, স্মল ওটা নয়।
আচ্ছা আচ্ছা হ্যাঁ বুঝতে পেরেছি।
The model without the intercept term.
ম্যাম
Yes.
ম্যাম যখন আমরা অ্যাকচুয়াল রিগ্রেশন রান করাবো তখন আমরা কি করে এরর গুলো দেখে বুঝবো যে ওটা পিওর সিরিয়াল কোরিলেশন না ইমপিওর সিরিয়াল কোরিলেশন?
দেখো, একটা রিগ্রেশন রান করাবার আগে না অনেক স্টেপস। ফার্স্ট উই নিড টু clean the data or plot the data, look at the data. So database preparation একটা বিরাট ব্যাপার থাকে। ওই database preparation এর সময় we consider, what is the relation between each of the x and y variable. We try to plot the matters. So it is not that having a data we will go for regression. So there will be number of before reaching to the regression. Regression is basically the last step of our analysis. Regression is basically the last step of our analysis. Okay, so when we do these things, we get, this is the probable relationship between y and this particular x. So from there we will have some idea about the relations, etc. Okay, so I told you when I'll be able to introduce the multiple regression model, then only I'll be able to tell you something about the omitted variable, how omitted variable bias appears in the context of regression, how we need to eliminate omitted variable bias. Okay, if there is misspecification, there are different tests by which we detect the misspecification. Okay, in our special course, next semester we have the software application too. Using Stata, we will learn how to capture misspecification, how to understand whether there is any omitted variable bias. So there are different tests. Now here we are discussing some tests by which you will detect heteroscedasticity, you will detect autocorrelation. Now parallelly, there are tests to detect whether there is any omitted variable bias or not. There are tests to understand whether there is any significant misspecification in the model or not. Okay, so there are many things in the background. So when you will finally tell, yes, this is the estimated demand for orange, before that you have to do these and that, so many steps. Okay, and then finally you will conclude this is the estimated demand for this population. Okay, Pratyush?
Okay, ma'am, understood.
Many things are there. We are learning a few, Actually, in the general syllabus too, we have the idea of omitted variable bias. We have the idea of misspecification. However, before that, we need to introduce the multiple regression. So how much I'll be able to proceed in this short semester, I'm not sure. Okay, so it will be not possible to discuss each and everything. I am still expecting that I'll be able to introduce multiple regression. However, I am not sure whether I'll be able to cover the different tests to detect omitted variable bias, different tests to detect misspecification. So I'm not sure this time. And you have to parallelly learn or grasp the matter. Okay, so I have only 3 weeks in my hand. And in the last week, maybe there will be the G final exam. Okay, so I don't have much time. Any other question?